Hello, I am Ed Pegg Jr., and welcome to another episode of Mathematical Games, a series where I talk about things related to the works of Martin Gardner, who did the Mathematical Games column in Scientific American for 25 years. They were collected into 15 books, and many mathematicians, including myself, found those very inspiring, and that's one reason I got into mathematics. So, one item I've always been interested in is geometry, and particular things that polyhedra and polygons can do, various tilings and tessellations, and many of those deal with the golden ratio. For example, the icosahedron has a lot of things based on the golden ratio. The pentagon is a shape where the diagonals have a ratio of a golden ratio to the edges. So when I learned more, I found these other constants that were related to the golden ratio that came up a lot, and I thought I would explore some of the discoveries I've made in this talk. In particular, these constants here, 2, phi, psi, chi, and rho, otherwise known as the number 2, the golden ratio, the super golden ratio, the chi constant, and the plastic constant. And all of these can be derived by looking at these sums. 2 is the infinite sum of the reciprocals of 2, starting with the zero power. And if you look at the powers for 1, 2, 3, and 4, the solutions are the golden ratio is an infinite sum of itself, starting with the first reciprocal. The super golden ratio starts with the second. The chi constant starts with the third, and the plastic constant starts with the fourth. And you get these 5 values. And here they are in a table, along with the minimal polynomials associated with them. The discriminant is something I use a lot in my studies, so I may as well talk about what that is. The number field discriminant for these values is 1, 5, negative 31, negative 283, and negative 23. And these are basically the squared volume you get from the polynomial. So here's one way of setting that up. So we've got this root here, and we set up a integral basis for it, which is something I don't completely understand, I'll admit. And when we do this matrix and take the determinant, we get minus 23. Now, the reason this is useful is because if you say add 7 to this root or change it in various other ways, there's a whole bunch of ways you can mess with this root object. But if you then take the resulting value and find its discriminant again, you'll always get minus 23. So when working with these values and you've got a geometry of points and lines, basically to know what space it's in, you basically just need to look at one length of something, and if that length is a strange number, say a third root or a sixth root or something, you can usually find out what it is just by taking its discriminant. So here's the case for chi. It's slightly larger. Note how in the plastic constant, this first column is powers of the plastic constant. For chi, it's the second values. The second column are powers of the chi constant. All of these have strange representations under radicals, the golden ratio is somewhat simple, but for the super golden ratio and the classic constant, I do not have these two values committed to memory, the radical form. I would not be able to go up to a blackboard and write those out. And the chi constant is somewhat ridiculous. It's much more complicated. So with an experiment I'll be mentioning later, I happen to notice this property was at the heart of all the values that popped up the most often in this one experiment I did. Gardner talked about the golden ratio, and in his later writings away from Scientific American, he did look at the plastic constant.
Chest down towards the ground as you swing. As you get better at this move, you want to gradually invert your gainer by pushing your hips forward and leaning back. Oh, Halloween's coming up in a week. You decide you want to
just a second.
Oh, you're in luck. Today, in 3 easy steps I want to show you.
I'm getting interference.
So you want to learn to flip, but the back looks too scary? Well, you're in luck because I'm going to teach you the this flip.
So I'll try to get around that. Sorry about that. So Gardner talked about the super golden ratio and the plastic constant in his later writings, but I wasn't able to track them down for this talk. So one place these come up is series. The golden ratio comes out as ratios between values in the Fibonacci sequence. And here's the writings of Fibonacci right here. This is a photograph of the book Liber Abaci, where you can vaguely see these numbers here. That's the first place where the Fibonacci sequence was written down. And he did that in what, 1202. About a century later, the mathematician Nirayama posed a similar question about cows, where they skipped 1 year, and that became known as the cow sequence, whereas the Fibonacci sequence was thought of as the rabbit sequence, because he talked about it as a problem related to rabbits. So those two sequences, the Fibonacci sequence, 1, 2, 3, 5, 8, where every value is the sum of the previous two, and the Nirayama, where every value is the sum of the previous three, skipping the middle one. Those became pretty standard sequences in. Let me put my headphones back on here. These became rather standard sequences for number theory, and then the exploration of number sequences. Many of those can be seen at the online encyclopedia of integer sequences, oeis.org. And we have these 6 sequences, all of which are the property that if you take a look at neighboring terms, they tend towards a particular sequence. So here's powers of 2 being used on triangles. We have the numbers in the center are reciprocals for the edge lengths. So here we have the edge length is 1, or 2 to the power of 0. Here the edge length is 1/2, or 2 to the power of -1, 1/4, 1/8, 1/16, and so on. And if you plot these out as triangles, you get this nice spiral effect as you look at powers of 2. If we look at the golden ratio instead, we get 2 spirals instead, and the same values here. This is basically the golden ratio to the power of -0, the golden ratio to the power of -1, the golden ratio to the power of -2, and so on. and you get this infinite spiral going in. For the plastic constant, you just get one spiral. And the same thing here. The first edge is the plastic constant to the -0, then the plastic constant to the -1, plastic constant to the -2, and so on. So that's a nice series to show how these three constants are interrelated. The powers of 2, powers of the golden ratio, powers of the plastic constant make this nice series of triangles. And it turns out that all of these constants can be used for strange tilings of progressively sized triangles. So here are all of the triangles with a 45 triangles in series. They have a total area of 760, and here's a area 761 triangle that has all 22 of those triangles, and there's just this one little square at the top which isn't a triangle. So this is a nice progressive series showing how well these 22 dissimilar triangles will all fit together nicely. The Kepler triangle is down here at the bottom. The golden ratio to the power 0, golden ratio, or the square root of the golden ratio to the power 1, and the square root of the golden ratio to the power 2. This makes a nice triangle as discovered by Kepler. And if we take a series of these numbers on the edges, those are powers of the square root of the golden ratio. So when you multiply by the square root of the golden ratio, all of the edges gain 1. So this is one way of spotting similar triangles using powers. All of these edges are powers of a certain root, and when you add 1, you get a similar triangle which is scaled up by that root. And these 6 triangles in progression will make up a triangle, and they all are similar triangles. So we can do that again with the super golden ratio with 7 triangles, as shown here. These are all scaled versions of the 0, 2, 3 triangle in the square root of the super golden ratio. The plastic constant also works with 0, 1, 3 as the powers for the triangle. And the chi ratio, I haven't been able to find a rectangle yet with a progressive series for chi, but this is a triangle that they make. These are also seen in constructions. For example, the golden ratio, we can start by making 2 circles, and then we draw this particular arc here. And if we draw a few more arcs, we can make a pentagon. So this is a classic construction of a pentagon, which can be used to find the golden ratio, which is one of these diagonals here. So for the plastic constant and the super golden ratio, those are based on cubics. And you can't do cubics with ruler and compass, but you can make them with origami. And here are the 7 axioms of origami. And one in particular is this 6th one: fold a point onto a line and another point onto a line, which happens to be the common tangent of 2 parabolas. So if you start with the points -2, 2 and -4, 1, and you have the normal y and x axes, you can basically fold -2, 2 onto the x-axis and -4, 1 onto the y-axis. And when you do that, you get a dotted line here, you get a fold that happens to be scaled for the cube root of 2. So these two lines here, the blue line has length 1, the vertical line has length of the cube root of 2. We can do another fold with -1, 2, and -2, -1. When those are folded, you get a golden ratio fold, where this line is length 1 and this line here is length the golden ratio. With the points -1, 2, and -2, 0, we get the plastic constant when we make this fold, as shown here. Start with -2, 1 and -2, 2 and make a fold onto the y and x axis. You get the super golden ratio, as shown here. As an aside, we can also make the heptagon with -1, -1/2, and 0, 1. Folding those gives these 2 points in this fold, which is one line of the heptagon. And we can also fold a nonagon with points at minus square root of 3, -1, and square root of 3, 1. Those nicely fold to a perfect nonagon. And you can reuse these 2 points in various ways. So one of my experiments was looking at power simplices. So basically, you take a series of lengths and you try to find how big of a simplex you can build where all of the distances are powers of a particular root. So here's an example of a 5 simplex, which happens to be representable in 2D space. All of these values here are powers of the square root of the plastic constant. So what a simplex is called when it exists in lower dimensions is something rather odd. 5 points are called flat if the hypervolume of the simplex is 0. This is also called a 3D degenerate simplex. And 4 points is called a plane if the bounding volume is 0, or also called a 2D degenerate tetrahedron. And you can also get a straight if they're just a straight line. So the terms of area, volume, hypervolume have a new set of terms if things get degenerate. And I did a demonstration where I looked for simplices that fit in 3D space. So here's one with the root of the plastic constant. There's a whole bunch here where they're roots of the plastic constant. And one thing I noticed with this experiment was that the plastic constant showed up a lot. Here I was trying to keep all of the powers at different values. Here's the chi constant popping up. So all of these numbers are powers of a root of the chi constant. And we get a few higher powers. But usually there's never too many solutions for those. Most of the solutions were back in the plastic constant or chi. So I decided I would redo that experiment for this talk. So a way to setting this up is you take the Cayley-Menger simplex, which is this matrix right here. When you basically just put in values here and square it, if this turns out to be 0, when you take the determinant, you have a degenerate simplex. So basically, if you set these all up to be powers so that you're taking, say, k to the power of these 10 values, which are integers. When you plug those in, you can solve for k and find out what roots would lead to 0. One thing that sped this up was there's 120 permutations to consider for canonical forms because there are 5 points. So by being careful about how you select permutations of these 10 values, you can vastly cut down the number of searches you need to do. And when I did that in canonical forms for all integer values up to 5, I found that there were about 440,000 canonical items to solve, and out of those, I was able to boil down to about 5,000 that had solutions. If anybody wants these canonicals, I can send them along, but they're not too hard to calculate. So one of the first things I separated out was the ones that fit on a plane, which I should have called planes here, because flats is 3D objects, but I keep getting flats mixed up with things being flat. So here's one of the simplices I found. It's based on the super golden ratio, and these are the powers. When you do this calculation, it should come out to be 0. Yes. So we can take a look at these. So here's the one I was just looking at, I think. Yes. So this object here in the space of the super golden ratio, this is a degenerate to the simplex. So let's take a look at these. We've got the regular pentagon. This is in the space of the golden ratio. And we've got more in the space of the golden ratio. Here's the square root of the golden ratio. You can see that I've used the discriminant here to identify all of these things fitting together into the same space. Nothing too totally interesting so far because there's multiple points on a line. Those are less interesting. Also, things with high symmetry are less interesting. So this is also symmetrical. So I found quite a few here based on the golden ratio. Here's a couple dealing with the square root of 2. And then here's the plastic constant. And then a whole bunch with the super golden ratio, which is something I did not expect. Because in the previous one I did, the plastic constant was the winner. Now we get the chi constant here. We get a few more of these flats, and then a few more values. I might have to look at -507 because I got a lot of solutions for this, and it's not on my list. But maybe it should be. And that was the last of them. So I might need to take a look at that new discriminant. So I wasn't expecting these super golden, so I decided to take a closer look. So here are the 11 super goldens. These might be involved in new tiling systems, so that's something I should take a look at. And we can ask how well do they overlap. So these are the first 3 put together in one image. This line here is not a direct power length, so I've put it in red. All these other values with numbers, those are powers of the square root of the super golden ratio. So I can put more of these together and look for cliques and try to find a clique where everything is a direct power. And it turns out you can get up to 8 with the super golden ratio, which is something I was not aware of. These others, this is a mirror reflection, and these others all have 7 points. But they still might be interesting. I might need to look at these further to see whether another point can be added for the 2D space for the super golden ratio. So all of these numbers here show what the distance is in terms of powers of the square root of the super golden ratio. So remember, my memo to self, flats are actually 3D objects, and here are the 5,850 solutions for degenerate simplices. And recall again that these are the values we're looking at, 2, phi, psi, chi, and rho. So when we take a look at what spaces these live in, the winner is the plastic constant with 961 solutions, followed closely by the super golden ratio with 853. The golden ratio came up next at 600 and something, then the chi constant at 571, and then 2 at 299. But I might have messed 2 up. I may have thrown out some solutions for 2. I'm not sure. I might have to redo that solution. And then there's a few more values that are used less. Some of these values are actually related to these constants here. One of them is the square root or cube root, and I forget what those are. I think 400 might deal with the cube root of 2. But none of these other discriminants have an algebraic space that are anywhere close to the main 5. And I basically started this talk a few weeks ago. This experiment was something I did a couple days ago. So I'm rather pleased that the results of this experiment show that these 5 values I said were important were actually important. They're right at the top of this experiment where I looked at everything. So here they are here. This is something I'll do it as a demonstration, and this will also be in a community post at community.wolfram.com sometime later today. So we can take a look at these. Of course, there's 5,000 of these, so I won't be able to go through all of them. But there's a whole bunch with discriminant 5 and discriminant minus 23. So here's one of the ones for the plastic constant. Some for the super golden ratio. And some for the chi constant. And then there's random others that might be worth looking at. I'm not sure. But I think the ones dealing with the major ones, the plastic constant and the super golden ratio, I think those might be important for something. And why do I think that? So here's what you can do with the plastic constant. In 3D space, we have a set of 19 points, which I call the plastic pyramid. Oops, this is not working. Well, let's see if I can make a better picture of this. I'm not sure that code will work. So I'll come back to that. So here's a set of 19 points. And when you look at the distances, all of them are integer powers of the square root of the plastic constant. So this is K19. And I think that was, I convinced myself that 19 was the maximal number of points with the plastic constant. And I believe that's true. But I also convinced myself when I did this experiment 8 or 9 years ago that nothing else could compete with it. However, this experiment I did a few days ago showed that there's a whole bunch I missed about the super golden ratio and the golden ratio. So I'm pretty sure that there's competition for the plastic constant. So I need to redo my experiment and see what the number of points is in 3D space for these values. So I call 19 the maximal flat degeneracy value for the plastic constant because this 19 simplex is degenerate, even with forced lengths. And I think that's fairly amazing that this would work, that all of these values would be powers of a certain root. I don't know of anything else like this in polyhedra. So that's something I want to explore more. These values are Pissot numbers. So here are the most here are the smallest known Pissot numbers, these values here. So I should probably say what those are. If you take a look at the complex roots of the plastic constant, it has 2 points inside the unit circle and 1 point on the outside. And it's a Pissot number if this real root is before this line at 2. So we can look at a few more. This is the super golden ratio, which is slightly larger. The closer you get to 2, the less interesting it is as a Pissot number. Here's a few more. I also have other polynomials of various sorts in here. Here's the chi constant here, where we have 3 points inside the unit circle. A Salem number can have a value inside the unit circle as well, instead of all points. You can have values on the unit circle instead of just inside. And with Salem numbers, you're also trying to keep away from 2. Oops, I may have crashed this. Uh-oh. I need to restart my talk. Just a moment. On screen is a character from my novel, Non Sequitur of the Equator. Let me get my notebook back up. Just a moment. I have to restart Mathematica here. Apologies for this. Okay. Where was I here? Oops. I forget how to go to a particular slide. Just a moment. Yes, clicking inside one of the manipulates doesn't help things. Almost there. So I was showing the Pissot, Salem, and cyclotomic polynomials. Let's go to the Mekhontev's wedge. So here's a non-trivial self-similar convex polyhedron where 8 copies will make a larger copy of itself. This was something found 3 days ago. It caught me unaware. It caught quite a few other people unaware. So this looks like it might be a new object, this 8 reptile. So here's what it looks like when we make extra copies of it. So how does this relate to 2? So 8 is the third power of 2, so that's one way. But there's another way that this really relates to 2. So we can make a larger mapping of it where we make 2 substitutions, and we get this object here. This is the level 2 reptile for the wedge. And we can go another level. So here's what it looks like when we just take the frameworks. And notice there's a point in here which seems to get used a lot, right around here. Turns out that's the point 321. So we can take a look at how that's used. In fact, it gets used 48 times. Here are all the wedges that use 321. Excuse me. Sorry about that. So it gets used 48 times, and it turns out that that's based on a cube. So in fact, with 6 of them, you make a side 2 cube with 1 cube missing. So basically, by taking a 2 by 2 by 2 cube, removing a cube, and dividing by 6, you get this wedge, which makes a larger copy of itself if you use 8 copies. And no one knew about this until earlier this week, which just amazes me. So this is a new object because somebody was playing around with a program. I'm thinking this should have been found years ago. So here's one experiment I did. I looked at the question, how can similar triangles surround a point? So here's one solution. We have these 4 similar triangles. These are all scaled powers for the plastic constant. And these numbers here are powers of the square root of the plastic constant, 0, 1, and 4. When we add 1 to all of those, we get 1, 2, 5. Add 1 to all those, we get 2, 3, 6. Add 1 to all those, we get 3, 4, 7. And those 4 triangles together will surround a point. So I wrote a program to find solutions for this, and these are the solutions it found. Here's one for the square root of 2. These objects here, and it looks like you could complete a triangle here and perhaps get something. So this is an interesting looking solution for me. That's what I thought when I saw this a few years ago after doing the experiment. I was like, maybe I can make some sort of substitution tiling system out of this. So let's look at more. This is everything has right angles, so this isn't quite as interesting. Same here. But this is based on the square root of the plastic constant. Oh, sorry, the square root of the golden ratio. You could complete a triangle with these just by extending these 2 lines. So that might be interesting. This might lead to a new tiling system. And here's another. I tried making a tiling system out of this, but I couldn't get things to work. But maybe I just missed it. This could possibly lead to a new tiling system, but I wasn't able to find one. Right angles, not interesting. And here's the one I started with. This is easy to extend to make 1 triangle, so that might be interesting. Here's another that might make a triangle, could be interesting. Right angles, no, who cares? Here's another, we could extend this to make a triangle. This might be interesting. This is based on the square root of the super golden ratio. More right angles. This could do something, who knows? More right angles. And here's another. This could make a triangle that might be interesting. So that's worth looking at. So I had these various cases, and I decided to start looking to see, well, there's 5 possible items here that I might be able to make substitution tiling systems out of if I'm lucky. And all of them relate to the series of values that are the sums of their own reciprocals. So maybe 2, phi, psi, chi, and rho are related in some way, dealing with tiling systems. And that was an incredibly crazy idea. There were no tilings based on these particular triangles known, but I figured I'm going to find new tiling systems. So here's one. This is the one based on the square root of 2. And we can complete it. We get this triangle here. It turns out that this edge here means it's not a 2D degenerate simplex. So I took a look at it. Here's a modified form, which I found easier to work with. And I found the tiling system. Here it is here. This object here is right there. And when I added more triangles, I got back to the original triangle. So this is a tiling system I called square root of 2. And here's what it looks like when you do it multiple times. Another triangle which is closely related to this is the 4, 5, 6 triangle. In fact, if you start with a 4, 5, 6 triangle and bisect both of the angles here and here, you basically automatically get this weird figure, which is all based on similar triangles. So not similar to the outer triangle, but all of these internal triangles are similar. And they're all based on powers of the square root of 2. And here's Mathematica solving this problem. We can just basically plug in values and it comes up with the solution for that. So one of the triangles I found in my experiment actually did lead to a completely new tiling system. Okay, here's the one for phi, the golden ratio. This is a weird one. This is how that solution look. And that is right here in this tiling system. I needed to add more triangles to this, but when you add these extra triangles, you get back the original triangle. So I called this the square root of phi tiling system. And here's what it looks like when you do multiple copies of it. So the next one was this one here, the one I showed first. This is seen right here in this tiling system. So I needed to add a few more triangles to it. This larger triangle here is also similar, but it's not scaled the same way. It's not an integer scale for in terms of powers for these other triangles. So I added a few more triangles, and that way everything was a nice integral scale for a recursive tiling. And here's what it looks like when they're done multiple times. So here's a mathematical solving the easier version, where the similar triangles here are the items seen in the solution here. So that's 3 successes out of that experiment where I came up with completely new tiling systems. Here's the one for the plastic constant, the square root of rho triangle. We've got these 4 triangles here, and they're right there. When you complete it, you get this isosceles triangle. And if you make another copy of that here, smaller, and add this triangle, which is the same as that triangle, you get back the original triangle, and everything is nicely scaled. So I called this the square root of rows system. And here's what happens when you repeat that item. It turns out that Andrzej Zak found this isosceles triangle earlier. And when you take these as 6 pieces, it turns out you can rearrange them to get this secondary solution for the triangle. I don't know of another case where really weird similar triangles that are not congruent to each other can make 2 different copies of itself. So this is a special case here. And here's geometric scene can also solve this problem. So that's 4 successes. And here's the chi solution, where I had this odd solution here. And it's seen right here. Extending the lines, you get this isosceles triangle. You can make a smaller copy of it here. And then when you add a few more triangles, you get everything is a similar triangle for the outer triangle, and everything is nicely scaled in integral relation. This is the square root of chi system. And here's a few iterations of that. So I basically went in with this experiment back here. How can you surround a point with similar triangles? I found some weird solutions that apparently weren't known to anybody, and I came up with 5 new tiling systems that no one had seen before. So here's a few more substitution tiling systems dealing with 2. We can take a look at duos where you've got more than one shape. So for example, these 2 here, most of these have more than 2 shapes involved, except for the 2 triangle. This is a fractal tiling system, which I'll cover a bit later. This is basically a 1, 2, 2 triangle, and this is a 1/2, 1, 1 triangle, 2 copies of it. And this outline here, if you look at this item, this is a 2, 4, 4 triangle, and this makes a fractal tiling when it's repeated. So here's the square root of 2 tiling is one of the self-replicating tilings associated with the value 2, as is Amen A4. Here are substitution tiling systems dealing with phi. The Amen chair, also known as the golden bee by Carl Scherer. Robert Amen and Carl Scherer both found this shape independently, and all the edges are powers of the square root of the golden ratio. The phi chair is a larger system. Kites and Darts by Roger Penrose, the Robinson tiles, and a couple others related to the Penrose tiles. And then there's the square root of phi system, which I found. Substitution tilings dealing with psi. There's the psi quad, which I'll cover. The psi chord quadrilateral, the psi wedge. The quadrilateral, the wedge, and the psi trap were all found by Dale Walton, as far as I remember. I've got the actual names in the demonstration substitution tilings. And here's the square root of phi psi system. These all deal with the super golden ratio. Then there's the plastic constant, which has these 4 substitution tiling systems associated with it. As they exist in my database, which has things that need to be added. So here's the square root of row system. And one I need to add is the plastic pentagon by Vesa Timonen. Here's how the powers of the square root of the plastic constant are set up on the edges. And I need to fix my code so that this diagram is more correct. So I need to do some code work and update my database on substitution tilings. We can look at rectangles for these objects. For example, if we remove a square from the golden rectangle, we get another golden rectangle, as shown here. And a series of square root of golden, square root of phi rectangles will make a square root of phi rectangle, as shown here. I mentioned here that the continued fraction for the golden ratio is a nice series of ones. And for the silver ratio, dealing with the square root of 2, we get a nice series of 2s. And A4 paper is based on the square root of 2. When it's folded in half, you get a rectangle similar to the original rectangle. So here's a 3-step series. This rectangle is similar to that one, and so on. And you can keep going with that. And in fact, if you have a area 200 sheet of A4 paper, you can divide it into a whole series of smaller A4 rectangles, as shown here, where everything is based on the fourth root of 2 in terms of placement. And all of these areas here are either a square or 2 times a square. For the super golden ratio, we get a square again and 2 rectangles scaled by the super golden ratio. And the plastic constant will make a square when everything is scaled. We can also look at self-representations. For example, this triangle has an area of 2. We can divide it into triangles with area 1, 1/2, 1/4, 1/8, 1/16, and so on. So this is an infinite series showing that the infinite sum of 2's reciprocals equals 2. Here's another infinite series for the golden ratio, starting with 1 over the golden ratio, 2 over the golden ratio, and so on. All of these together add up to a triangle with an area of the golden ratio. The super golden fractal triangle, as shown here, has the same property. An infinite series will add up to itself. And the plastic fractal triangle also has the same property. An infinite series of copies of itself scaled will add up to the plastic constant. For nice triangles, if you look at, say, the 1, 1 square root of 2 triangle, I'm representing things in terms of powers, you get the 45, 45, 90 triangle. And the Kepler triplet triangle, 1 square root of phi, phi, was found by Kepler. But there's other triangles that also have 90 and 60 degree angles, as shown here. For the plastic constant, you get these triangles. For the super golden ratio, you get these values. And some of these we saw in the triangle experiment I did earlier. I mentioned those are right angles. Nobody will care about those. Well, they're still nice triangles. And in fact, one particularly nice one I like is just the simple powers of psi, the super golden ratio. Just the simple powers 0, 1, 2 will make a triangle where one of the angles is 120 degrees. So if these triangles can be hit within a tiling system, something nice might happen because 4 or 6 of them might fit together. Which is something we can see with tetrahedral similarohedrons, where all the faces are similar to each other. So here we have items based on the square root of the plastic constant. I think that would be which triangle? Maybe this one. Minus 0.32. So with this tetrahedron, we have a whole bunch of right angles popping up. As seen here. But we can vary this length and get different tetrahedron. So basically, as I change the root, the way this object looks changes. We can also look at the octahedron. These are all based on similar triangles. And as we change the root, we get different shapes. So whether these will fit in nicely for a tiling system depends on the angle that's generated by these. For the chaos game, I'm not sure why these have different sizes. For the chaos game, we basically just repeat something randomly and see where the points wind up. And for certain systems, you get shapes emerging from the points as you just randomly place points. So this is making a Rousey fractal for the super golden triangle. And here's the wriggly edges for making this object. So this is the psi triangle or super golden fractal triangle, where two copies of itself makes a larger copy of itself. There's also something similar for the plastic constant. And here's the wriggly edge version of it. There's code for all of these that will be in the notebook at community sometime later today. So for looking for other Rousey systems like this, one program is IFS tile by the person who found the wedge I mentioned earlier. He was playing around with this program and he happened to find that nice 3D wedge, which is 1/6 of the 2x2x2 cube with one cube removed. He was using that program. He found that it would make copies of itself. This is a quadrilateral I mentioned. So if we just take the super golden ratio and we take a look at one of the complex values of this, and we just look at the powers of that complex number, here's the 0th power, the first power, the second power, the third power, the fourth power. And if we add in the origin and the negative of the second power, we can draw a quadrilateral for the 0, 1, 2, 3 powers, and we can split it into two more quadrilaterals using these extra 2 points. And it turns out this makes a fractal tiling system. The plastic constant, you can do the same sort of thing. The 0th, 1st, 2nd, 3rd, and 4th powers, you can use those to make another tiling system, which I call psi quad and rho quad. And I mentioned the 2 triangle is also related. Using these triangle systems, you get another fractal substitution system. And none of these 3 were known before. I just happened to find them randomly after the triangle experiment. Many polyhedra use 2 phi or the Fibonacci constant. So here's one weird property of the truncated octahedron. If we take a look at it and then take a look at the distances between points, the complete set of distances squared is 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9, and 10, which is a very strange property for a polyhedron. I don't know of any other polyhedra like it, regular or otherwise. If anybody can find a polyhedron of a certain number of points for all the diagonals go up to 15, squared distances go up to 15, I'd very much like to hear about it. So here we have the Tetranacci constant and something weird based on the Tetranacci constant and phi. So a whole bunch of polyhedra in the octahedral group use 2. The cube octahedron are all based on 2. In the icosahedral group, they all use phi. And there's also the snubs, which is the Fibonacci constant. And these are here. And I show that we can construct the snubs with just a single root. So I use the Fibonacci constant here to construct all the faces of the snub. Oops. Let me get that back if I can. Oh, it looks like it doesn't want to cooperate. Got the paste. Oops. Nope. So for some reason, the code doesn't want to work now. But with just a single root, we can use the Fibonacci constant to make the snub cube. Oh, here it is. And by using, instead of -1, using the golden ratio, we can construct the snub dodecahedron. These are very complex objects. So if you take a look at them and at their vertices normally, but it turns out they can all be simplified to a single root. And here's pictures of all of these polyhedra. But there's one more, the snub icosahedron. This uses the plastic constant. And the circumradius is this value using the plastic constant. A couple more things about 2. If you look at a polygon where the edge length is 2, and then you take a line and divide it up by the diagonals, by the horizontal diagonals, the distances squared will add up to the number of sides of the polygon. So for 20, these 20 values here will add up to 20. And this works for any regular polygon. These values, 1 plus 3 plus 4 plus 3 plus 1, add up to 12. So for any regular polyhedron, you can determine the number of sides it has by going through this complex process of getting distances and squaring them and adding them together. Another weird property related to 2 is if you take a annulus, it always has the same area as the central red disk for any regular polygon. The inner circle and outer circle of that side 2 polygon, when you take the area of the green object, it's the same as the unit disk. I was trying to define things like this where everything always related to the golden ratio, but I wasn't able to find something. So one reason these show up in a lot of Rousey fractals is because psi and rho are very simple matrices. These are the eigenvalues for this matrix. So this is the super golden ratio. And for this matrix, this is the plastic constant. And it's the solution for square root of 1 plus 1 over x, when x plus 1 over x. And x equals 1 plus x. So these are 3 standard problems that happen to have these values. The 29th power of the plastic constant happens to be very close to this integer. This is a property of Poisson numbers, where you can get things that are very close to integers. And for example, for the super golden ratio, the 33rd power is very close to an integer. And powers of the golden ratio are always close to Lucas numbers. This is just one particular power, but pretty much any high power, you'll get something very close to a Lucas number. So there's a couple things that I'm still trying to solve. My original experiment, how can similar triangles surround the point? Well, it seems that I missed a few. So it's possible that there are nice tiling systems that I completely missed, or one of those other solutions might be of interest. How can similar tetrahedrons surround a point? This is something I still don't know. In the list of degenerate simplices, which ones overlap? So that's something of a larger study that I'd like to try out. Is the maximal flat degeneracy value for the plastic constant, is it actually 19? And what is the maximal flat degeneracy value for the super golden ratio and other constants? So those are a couple questions that I came up with after putting this talk together. And that's what I had. Many thanks for attending my talk. Let me see what questions have developed. Let's see. I don't see any questions that I can immediately answer here. Feel free to write to me if you have any comments. And many thanks for attending my talk. And we'll be back next month. Many thanks.